This episode is brought to you by Brilliant. Imagine you took the most reliable internal combustion engine based car of modern automotive history and displayed every single assembly line component it's made from out in front of you. Among these parts, which would you guess is the most stressed component within the entire vehicle? The most obvious conclusion would be the parts that transmit mechanical energy, such as the pistons, the crankshaft, or transmission components. Another possibility would be the spark plugs, which are directly exposed to thousands of hours of combustion. However, when you consider their application, most of these components are designed around one highly specific design goal. Mechanical components, for example, use mass and shape to transmit energy in a very specific manner under highly controlled conditions. Spark plug tips, on the other hand, are made of materials that can easily handle the specific goal of retaining their function when engulfed in combustion gases. This specificity makes it relatively easy to engineer a less stressed part. But what happens when you throw several competing design requirements at a component? One that must cope with volatile fluids at different temperatures and flow characteristics, as well as the high temperature and pressure of combustion. And on top of this, it must also deal with years of constant thermal cycling, all while being compressed under several tons of clamping force, and being less than a millimeter thick. This is the story of the most tortured component within the average reciprocating engine, the head gasket. A modern head gasket is an intricate hybrid mechanical seal, engineered to fill the space between a reciprocating engine's head and block. And while a head gasket does perform several functions, it's technically not a seal, as seals are used on moving components, while gaskets on static ones. In its contemporary form, a head gasket must meet four primary requirements. A head gasket must seal the passages that carry engine oil between the block and the head. Engine oil can vary dramatically in viscosity and temperature, ranging from the extreme lows of frigid ambient temperatures to as high as 135 degrees Celsius or about 275 degrees Fahrenheit. These temperature ranges can make engine oil as thick as syrup to as thin as water. Engine oil is also pressurized within a running engine, ranging anywhere from 1.4 to 5.5 bar or 20 to 80 psi. In addition to thermal cycling and the microscopic motion from combustion pressures, the sealing material must cope with the degrading nature of many of the additives found in commercial engine oils. Similar to engine oil on most water-cooled engines, a head gasket must also seal the passages that carry engine coolant between the head and the block. When compared to engine oil, engine coolant has a relatively consistent viscosity, with a lower maximum temperature of around 120 degrees Celsius or about 250 degrees Fahrenheit, with normal operations seldom reaching above 140 degrees Celsius or about 220 degrees Fahrenheit. It also operates under lower peak pressures at around 1 bar or about 15 psi. Much like with engine oils, the materials that seal engine coolant on top of thermal cycling and movement must deal with the corrosive properties of engine coolant. Nearly all water-cooled engines use coolants composed of a base fluid mix of either ethylene glycol or propylene glycol and water. And while this mixture does not directly attack seal material, it can generate corroded solid particles which come off the surface components within the cooling system and both interfere and erode seals along its flow path. Engine coolants are formulated with corrosion-inhibiting systems that attempt to form a protective layer that insulates metals from coolant contact. These range from early inorganic oxide additives such as silicates, phosphates, and borates to more modern extended-life carboxylate-based coolants that provide superior corrosion resistance. Sealing combustion gases are by far the most brutal and critical requirement of a head gasket. These gases can peak in pressure at around 6.8 megapascals or about 1000 psi for the vast majority of vehicle engines, though pressures as high as 15.1 megapascals or about 2200 psi do occur in higher performance engines. Diesel engines experience even higher combustion pressures, easily operating in excess of 18.6 megapascals or about 2700 psi. In gasoline engines, abnormal combustion conditions can also create huge spikes in pressure. Detonation, for example, can easily raise combustion pressures past 24.1 megapascals or about 3500 psi. These bursts of pressure produce tiny amounts of motion called head lift that pull the engine's surfaces away from the head gasket by as much as 25 microns or about a thousandth of an inch in the most extreme circumstances. Combustion gases can also vary dramatically in temperature based on the engine's load. While combustion temperatures can easily reach above 2500 degrees Celsius or about 4500 degrees Fahrenheit in the region concentrated around the flame kernel and its subsequent flame front, the insulating effect of the surrounding gas in combination with the engine's cooling system tends to limit the temperatures reached at the cylinder surface to anywhere between 250 and 700 degrees Celsius or about 480 to 1290 degrees Fahrenheit. While a head gasket must seal combustion gas from the surrounding coolant and oil passages, its primary function is to effectively contain the pressure of the combustion process. A head gasket forms part of the combustion chamber, and if this seal is compromised, the effective cylinder will lose the ability to produce a normal combustion sequence. Depending on the nature of this failure, the cylinder may consume or cross-contaminate other engine fluids. A head gasket must be deformable enough to maintain a seal between the imperfections of the head and block surfaces. These imperfections are quantified by the measurement of their peak-to-valley surface height as a roughness average, or RA. The lower the RA, the smoother the surface. Beyond surface imperfections, head gaskets must also contend with the expansion and contraction of the parts they seal as they heat and cool, and their own thermal motion from the variety of temperatures that they're exposed to. This becomes especially challenging on engines that use different metals or alloys for the head and block that create different expansion rates. They must also cope with the repeated motion of combustion forces pulling the head away from the block. In addition to these forces, head gaskets have to function under the dynamics and extreme mechanical stresses of combustion pressure. The head bolts that fasten the head to the block are typically not symmetrically spaced, creating an unevenly distributed clamping force across the gasket, with each of these bolts exerting a force of up to 45 kilonewtons or about 10,000 pounds. The head gasket must be capable of both not crushing, but also remaining dimensionally stable when exposed to these extreme thermal and mechanical stresses. Beyond these expectations, they must also be durable and capable of lasting across a significant portion of the engine's life with little to no maintenance. The modern head gasket evolved from gaskets that were used within steam engines since the advent of the Industrial Revolution. With the introduction of the internal combustion engines in the 1860s, almost every type of elastic material ever used within steam engines was experimented to seal combustion. Some of the more popular early materials utilized for gaskets were leather, paper, various soft metals, cork, and vulcanized rubber. As the internal combustion engine transitioned from its experimental early years to a mass-produced power plant, copper would become a popular material for these early head gaskets. When heated and allowed to cool slowly or annealed, copper softens and its ductility and toughness is improved. This conformability made copper sheet an excellent gasket material. However, early copper gaskets suffered from sealing issues due to copper being incompressible. This effectively made the gasket a copper shim. As both the copper gasket and the engine components experienced heat cycling and combustion stresses, their relative motion would create inconsistencies in the clamping force along the gasket's surface. This allowed combustion gases and liquids to eventually seep through. While regular retorquing of the head bolts could re-establish the seal, these early head gaskets remained unreliable. This was such a problem that in the early days of motorsports, head gasket failure was the most common reason for race cars to not finish a race. Oil leakage was so prevalent at race events that it was not uncommon for sand to be applied to the racetrack. Sealing would dramatically improve with the introduction of copper-clad gaskets. These gaskets sandwiched a compressible material such as rubber, compressed asbestos, or compressed cellulose fiber between two sheets of copper. This retained the advantages of the conformability of copper against the engine surfaces, but made the gasket more resistant to expansion and contraction due to the springiness of the inner compressible layer. However, head gasket designers would now have to design the compressed thickness of the gasket to carefully match the engine's requirements and the clamping force of the head bolts. As the automotive industry began to flourish in the 1920s and 30s, less costly, mass-production-friendly head gasket designs were explored. One durable yet relatively inexpensive option was the steel shim head gasket. While extremely resilient and less susceptible to seal loss from heat cycling when compared to copper, steel shim head gaskets required a copper coating to properly seal against surface imperfections. However, they did suffer from corrosion issues, especially from coolant flow that would ultimately degrade the gasket's ability to seal over time. Around this period, A new technique to add compressibility to both copper and steel shim gaskets, called embossing, was developed. Embossments are stamped raised regions on critical sealing areas of a gasket that create a smaller contact point. This not only directed more force into the sealing action of the embossment, but also created a degree of spring to it, making it more resistant to seal loss from movement. However, despite these advantages, early gasket embossing tended to be too costly for mass production, and in some circumstances, it even needed to be done manually. After World War II, the introduction of the beater-add process would transform the gasket industry. In this process, a mixture of water, elastomers, fibers, graphite fillers, and binding agents are formed into a slurry. The slurry is then run through specialized machinery that extracts the water, then dries, compresses, and vulcanizes the material into long continuous sheets that are ready for gasket fabrication. Some of the elastomer blends used include latex, nitriles, styrenes, acrylics, and fluorocarbons, with asbestos fiber being a common substrate. The beater-add process offered a new, lower-cost gasket material option that would lead to manufacturers eventually introducing the composite head gasket in the late 1940s. Composite head gaskets consist of either a perforated or solid steel carrier sheet, onto which the beater-add slurry is rolled onto both sides. Metal beads called fire rings are created within the gasket's metal structure to seal the combustion chamber and protect the elastomer material from overheating. The non-metallic surface of the gasket is then impregnated with a silicone-based agent to seal any pores and prevent the gasket from swelling when it comes in contact with liquids. Some designs may even incorporate seal elements made from a high-temperature, chemical-resistant fluorocarbon-based elastomer material called Viton that are fixed to fluid channels on the gasket, enhancing the gasket's seal and degradation resistance. While composite gaskets can form easily, are compressible, and have excellent mechanical strength, the nature of the beater-add coating makes them highly susceptible to the mating surface quality, cleanliness, and overheating. They generally require highly parallel block and head faces, with an average surface roughness of about 1.52 to 2.03 microns. This is roughly equivalent to a sandpaper grit finish between 120 and 160. Rougher surfaces limit gasket conformance, while smoother surfaces increase the tendency for the gasket to flow and reduce its blowout resistance. Because of its reliance on its surface coating for sealing, composite gaskets are easily compromised by being pressed into dirt or foreign objects. They also rapidly degrade when exposed to abnormal engine conditions, with the two most common modes of failure being composite swell from the steam of overheating and combustion seal failure from both overheating and detonation. Much like copper-clad gaskets, the compressibility of a composite head gasket is carefully matched to its application and the clamping force of the head bolts. In 1970, Japanese gasket maker Ishikawa was issued the first patent for a revolutionary new type of head gasket called the multi-layer steel or MLS head gasket. MLS head gaskets are made from 3 to 7 layers of embossed stainless steel shims that are riveted together, with 3-layer gaskets being the most common configuration. These embossments, when sandwiched together, form a sheet spring that can easily expand and contract in a highly controlled manner. The outer surfaces of the gasket are typically coated with a thin fluorocarbon-based Viton layer in targeted areas to aid in surface sealing, especially for liquids. Because MLS gaskets are made from layered sheets of steel, they can more easily be manufactured to specific thicknesses and spring rates that allow engineers to more easily adjust a head block gap for specific compression needs or valve train geometries. Their springiness also makes them relatively forgiving in respect to surface flatness. They can easily tolerate surface deviations of up to 1/10 of a millimeter. However, the sealing coating on their outer surfaces generally require a smoother 0.76 to 1.52 micron average surface roughness, or about a grit finish between 180 and 120. This spring effect is so resilient that MLS gaskets are capable of tolerating combustion forces that can lift a head as far as 25 microns or about 1/1000th of an inch from the block. This also had the side effect of requiring no head bolt retorquing maintenance. This layer structure even allowed for additional mechanisms to be embedded within intermediate layers of the gasket, especially for performance applications. These may include structural or coating modifications to enhance conformability to a stopper layer that provides a more positive seal against combustion pressures, similar to a fire ring. MLS gaskets were initially introduced to the market on Japanese vehicles in the 1970s and 1980s, with Isuzu being the first to adopt the technology in Japan. By the 1990s, American manufacturers began to use MLS head gaskets in their engines, with Ford being the first major adopter with their 4.6-liter modular V8. Today, the unmatched superiority of MLS head gaskets in terms of performance to cost have made them an industry standard, being found on most modern vehicles and even in many performance applications. However, despite the success of MLS technology, other less common head gasket technologies still exist, though these target highly specific needs such as extreme performance or cost cutting. The elastomeric head gasket is an example of a cost reduction focused design. Found on a handful of mid-1980s to early 1990s British vehicles, these gaskets used a single steel shim with a beading coating of an elastomeric material such as silicone or Viton for fluid sealing. These gaskets may sometimes employ a fire ring style embossment on their steel core. While easily and inexpensively manufactured by die stamping, these head gaskets prove to be generally unreliable due to their relative lack of elasticity and heavy reliance on the elastomer coating for sealing, especially when compared to MLS head gaskets of the time. On the opposite end of the performance spectrum are modern solid copper head gaskets. Found almost exclusively in motorsport use, especially within high horsepower engines, these solid copper gaskets differ from their counterparts of the past primarily in how they seal the combustion chamber. An engine must be specifically designed around their use, incorporating a special machined receiver groove within the block and sometimes heads for each cylinder. These grooves carry a stainless steel O-ring that, when combined with a solid copper head gasket and a spray-on surface sealer coating, is capable of sealing in some of the highest combustion pressures found within reciprocating engines. While not specifically designed for the longevity needed by production vehicles, these head gasket systems are reusable and easily support both the extreme power and frequency of teardown found in race engines. At present, MLS technology will likely be the final evolution of the head gasket as the automotive industry slowly embraces the coming transition away from the internal combustion engine. Though the need to contain the power for reciprocating combustion will likely still exist for decades to come. Sealing at the extremes of combustion took decades to perfect, with the experimentation of materials at their limits being crucial to development. If you want to build a similar intuition for physical problem solving, you should check out Brilliant. Brilliant is an incredible way to master math, computer science, and engineering because it focuses on helping you truly understand the concepts rather than just memorizing them. It's built on the belief that you are a problem solver. You just need the right tools to unlock that potential. Instead of sitting through passive lectures, you learn through interactive, hands-on challenges that get you to those breakthroughs in understanding. And with their larger content library and personalized practice sets that adapt to your progress, you'll always be challenged at exactly the right level to keep you growing. You'll also be confident that you're learning the right way because Brilliant is handcrafted by an award-winning team of teachers, researchers, and professionals from MIT, Harvard, Google, and more, harnessing that expertise to design personalized practice sets just for you. And speaking of problem solving, I highly recommend checking out Brilliant's scientific thinking courses. It teaches you the critical skill of forming and analyzing connections in the world around you by solving puzzles with science. To start reaching your serious learning goals, go to brilliant.org/newmind or scan the QR code on the screen. The link will let you learn for free on Brilliant for a full 30 days. Brilliant is also giving my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything they have to offer.